relatively easy to get, the second derivative test would be a lot quicker to do. Goodbye, Ruby Tuesday. Okay. Gotta get all old school today.
I've been doing homework 8 o'clock this morning. Because the first class that I had today was canceled because he had a family emergency. And then the one he was canceled. So this is a little I was not here. I talked to my mom last night. I got the news about
Everybody got their test back, yes?
my first class last night.
Does anyone have any questions at the moment?
While I was at
Yes.
with her, so that she could drop me off, because she was just
What's the secretary to tell you?
She picked up the notice of warning.
Well, okay, so you can go down that route, but what does it tell you? Just immediately, directly, not two layers.
Leaving, and so that's pretty simple.
No, that's the first derivative. It tells you this slope's positive, this slope's negative. What's the second derivative tell you? Concavity. If the second derivative is negative, what does that mean the graph looks like? Yeah, like this. Now, if the second derivative is negative, add a critical number. What does that mean about the critical number? It's math. So all you have to do for the second derivative test, get your critical number for the first derivative, get the second derivative, plug those in. If the second derivative is negative, that's a negative. Second derivative is positive, that's a negative. Yes. Yes. Yeah. Okay. That's great. Anything else, guys, from the test? Anything, and of course, if you see anything on in the grades I put up there that seem wrong, let me know. What's up, Brandon?
Okay. So basically, so none of the questions that you asked were graph, right?
None of the questions were.
You know, find this, show that this derivative, blah blah blah, or like, you know, find the max and min, inflection points, and all that.
Sure. All that jazz, yeah.
Yeah. So the second derivative does not help you in that, like at all.
Of course it does. If I ask you for inflection points, that's second derivative test. I mean, a second derivative. That's where you do the sign diagram of the second derivative. You see where the concavity changes. That would be an inflection point where it changes. Yeah.
So can you do basically what you did for what is it, problem 2 or something? Can you do something like that for that?
Again. All right. So, couple things. Second derivative test. So second derivative, guys. What does the second derivative tell you?
Concavity.
Concavity, right? And I always love my students. It's like, it doesn't say anything, Japanese no shut. So it tells you what a concavity is. If I have a critical number somewhere, and the concavity through that point is negative, that critical number is the location of a
Max.
maximum. So how do I utilize a second derivative test? Take the first derivative, take the critical numbers. That's all the places where a max or a min could occur, yes. That's the definition of a critical number, is all the locations where a max or min might occur. Plug those into the second derivative and just see, is it opening up? Min. If it's opening down, max.
Is that your reflection?
Does that have anything to do with the inflection point? I don't give a shit about where the concavity is changing. All I want to know is whether the maxes and mins are. So let me ask you, if I have this, what's true about my thumb? What's that the location of?
An inflection point.
Inflection point. If my question is, where's the max and the min? Well, where's the max and the min?
At the top of
Top of that? Bottom of that, yeah. Miles away from the inflection point. It doesn't matter where the inflection point is. I need to know, guys, at a critical number, is the concavity positive? Then it would be a min. Is that straightforward? If the concavity is positive through a critical number, it must be a min. If the concavity is negative through a critical number, it must be a maximum. Because one is at the bottom of the valley and the other one's at the top. That's all the secondary test is. Okay. Another big thing. Two things I want to talk about. So I don't know, guys. Let's say I have a function that looks like, I don't know, this. I don't know. And I say, and you're all like, yeah, Jeff, you're fun. I say, I want you to graph this in the first quadrant, right? So all I care about is first quadrant. That's all I care about. All I care about is first quadrant, that's all I said. What are two immediately really smart points to get?
4 and
X and Y intercept.
-4.
Careful.
Sorry.
That would be a
4.
vertical asymptote. What is the X intercept? 4.
4.
How did you know it so well? Because 4 makes it 0. You can see it. What's the y-intercept? How do you always find the y-intercept? You make x 0. So what's the y-intercept? 1. And then you can pick a point if you want to, anything in the middle. So if I put a 2 in, I get 2 over 6. That's 1/3. So at 2, it's about 1/3. So then I get this graph. Whee! And a lot of people did too much. You had some other shit going on. That's fine. As long as you focus on the first quadrant. Now, after doing the homework, everybody should know what the word inscribed means. Right? It was really, really obvious that some of us had no idea. So, somebody did come up and ask me, and I just drew a little picture. Say, remember the problem we did? No. Oh, look at this. So whenever there's something, just come up and ask me. I'm the only person you can't ask. So might as well ask me, right? At the very worst, I'll just say, I'm not going to tell you. And you're like, okay. And then you walk. Okay. What does inscribed mean? So I want to inscribe in that function in the first quadrant. So what walls does my rectangle have to live within?
The line and the x and y.
The function and the x and y axis. So what's the only way? I mean, there's several. Do you guys see how there's several rectangles I can draw that does that?
Mm-hmm.
It's got to touch my y-axis, it's got to touch my x-axis, and it's got to touch the function. So one I could draw would look like, yes? Or I could draw, or I could draw, it doesn't matter which one you draw. What is always true, one corner of it is going to sit on that function, yes? So what point is any of these?
X, Y.
X, Y. And what's Y?
The 4 minus x.
Yes, okay. Now, here's the thing that really, no matter what the problem is, it's got a stupid thing living inside something else, and you're like, oh my God. It's got, some dude trying to put fencing and it costs money. It's got freaking somebody filling up the thing, whatever the shit it's got. If I'm asking you to maximize or minimize blank, your entire focus should be on making that function. Because if I knew the function that represents gas mileage, if I had that function and I wanted to figure out what's the maximum gas mileage, what would I do with that function? Take its derivatives and find the critical numbers, yes? So I can't answer a question about maximizing or minimizing something until I get its function. Then I can attack it, yes? Then I got this calculus I can attack it with. So now, some of you guys got the picture drawn. Some of you guys have the rectangle living all over the damn place, but some of you guys got to this step, and then you sort of like, I don't have a clue, Jeff. But now the question is maximize the area. So let me kind of focus on one of these possibilities. Everybody had something like this. Draw like a little rectangle. For this one, it would be this business. So now I'm focused on what's the area of this. Well, what is the area? How far is this? X. And how far is this? Y. So my area is X times Y. But what do I know? What do they tell me?
Is this the Y piece?
I can replace Y with
4 minus X over X.
Yeah. Now, somebody got to this point. I'm not going to name your name because I forgot who the hell it was. And then you did like a product rule derivative. No. Multiply that X on the top, and then you just got a chain rule. A quotient rule, right? You guys can multiply the X on the top. Is that all right? And then you just take the derivative, set it equal to 0, or see where it's undefined. Get your critical numbers. Is that okay? Okay. So that's number whatever the hell. That's second to last one. 7. Thank you. Now, can everybody take out a blank sheet of paper if you don't already have a blank sheet of paper? It's exactly what I'm do right now, Jeff, is whatever you want me. Okay. So let's say I have some little person on a bike. I don't know. Can you somewhere in the middle of the paper just put a dot that represents the little kid on a bike? Yeah, little kid on a bike. Little kid on a bike, there he is. We're really far away, or we kind of made a snowball out of him. I don't know. In physics, we do that a lot. We just compress everything into a single point. Sounds painful. We will eventually, but I first got to show where the sides of the triangle come from. So, several things were happening in this crazy-ass problem. Where was there a balloon? Where did it start?
It was
so many feet above the kid, yes? Yeah. So some of you guys had 19, some 22, some 20, whatever the shit. There's several different versions of the test. So I'm going to draw a similar little thing here for the balloon, yes? Now don't get me wrong, I love the balloon, and then, because on my answer key I had a little dude on a bike, and blah, 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 so we're going to get there. Okay. Now the little dude on the bike, he's going, right? He's going. So can you draw a line that represents where the dude is after some time? Draw a line that would represent the distance he's gone, where he is after some time. And it didn't really say which direction he's traveling, but I normally just pick this way just because you could go that way, it doesn't matter. So at some time later, he's over here. Is everybody with me? Again, you could have drawn it that way, it doesn't matter. Okay. What about the balloon? Sometime later, what's the balloon doing? Going straight up. So how high is the balloon? Draw something that shows me the height of the balloon. It would be here, right? At some later time, at some arbitrary time in the future, it's going to be there. So my little dude is here at some time in the future, and my balloon is here at some time in the future. Can you draw on a line that represents the distance between the balloon and the boy and the bike? A lot of B's in this problem. The boy and the bike and the balloon. Believe in the boy and the bike and the balloon. So, have you got a line drawn? And of course, like Wyatt said, what's wrong with you people? Just make a triangle. But now we got a triangle. Okay. A lot of you guys got the triangle, and then you started putting numbers on the triangle. No. The minute you got the physical situation drawn, what do I do next?
Identify your DTs.
You could do that, but related to this immediately, I need to identify my variables, and then I can see the relationship between them, right? I need to identify, are only certain parts of this picture changing over time? Like if I had the one with the airplane that was a mile up and it just goes, that stays a mile, correct? Does any part of this triangle stay the same size over time? Nope, every damn part's moving. Balloon's going up, kid's going over, and so their length is changing also. The whole freaking thing is changing. So every single side needs a variable. Yes? You can call them whatever the hell you want to. Me, I'm boring as shit. So I say this is X and this is Y and then it's a C because it's the next letter. But you could use A, B, C, you could use whatever. I highly recommend you don't use D because then DD gets weird. Brings me back to Dexter's Lab. Now some of you guys, I'm not really sure. I'm not sure. Some of you kind of got the derivative of the function came out of nowhere. It wasn't quite right, but you never wrote the function now, which really trips me up. I'm like, did you memorize something? I don't know. But what's the relationship? Like Louis said, now that I've got all of my variables identified, this is everything that the problem refers to. Either distance-wise or rate-wise, this is all it refers to. How are they related?
Pythagorean theorem.
Yeah, Pythagorean. That's right. Good old Greek, dude. Good old Greek. I wasn't making fun of you, I was making fun of you. So x squared plus y squared equals z squared. Now, I think Wyatt said this earlier. Before you did this, after you did this, in the middle somewhere, now that I've got my variable set, I can now identify what dy dt is, dx dt. I told you what these were. Some of you it was 3 and 2 or 4 and 3 or whatever the shit, yes? You with me? So I'm going to pretend like it's 5 and 6 feet per second. It doesn't matter. What would this be then? Be very specific. What is this related to?
The balloon's height.
How the balloon's height is changing over time. Kick ass. And this, of course, is how the kid's position is changing over time. I love it. Kick ass. And what is it that we're trying to solve for?
The change dz over dt.
dz over dt. So symbols for what I tell you, symbol for what I ask you. So you know what to look for after you do your calculus. Okay. So some of you guys, I think you just, it's interesting. I feel like some of you guys put yourself in the middle of the problem. And then you try to kind of like work from the middle and go out like back to the beginning and then forward. I'm not sure how to describe this, but you kind of know what it's supposed to look like. So you kind of try to make it look like that. But you guys see how I let the problem set itself up. Kid's gotta move. Balloon's moving. This is what it wants. Okay, I got a triangle. Everything's changing. Okay, everybody gets a variable. Now I can identify, now that I've got variables, I can use symbols for what the shit they tell me. I can use symbols for what they ask me. So what am I gonna do with x squared plus y squared equals z squared now?
Solve it for one of the variables.
Take the derivative. Yeah. Take the derivative. Now, just to go one more step. What's the derivative? What do I get? Each one of these is gonna look the same, yes? Just with different letters. So this will be 2x
dz dt.
dx dt.
Or dx, yeah. Plus 2y
2y dy dt equals
2z
2z
dz dt.
dz dt. Yes, and I can kill the 2s if I want to. Some of you guys didn't. That's beautiful. You're all like, I'm not going to kill him until I have to. Or 2. I would just immediately kill the guy. He's done horrible things. Dx and dy dt, both of those I told everybody, yes? dz dt is what you're supposed to not know. So what is it we don't know that we're supposed to know? No. dz dt is what we're not supposed to know. We're trying to figure it out. Z, X, and Y. So again, you're all like, oh yeah, I see. This seems like a problem you would love, Jeff, because there's so many beautiful layers.
But they gave us time.
Yeah, I give you how much time has gone by. So if on this problem I said 4 seconds had gone by, how far has the kid rode? 4 seconds have gone by. How far has he gone?
24 feet.
24 feet. Now, I think 6 feet per second would actually be a little fast for a little kid, but I try to make your rates of change actually physically reasonable. Right? Anyway, sorry. The balloon height's a little bit harder, and if that was the only mistake you made, I just took off a point or something, but the balloon started off at a certain height, yes?
Yeah.
So if my balloon started off 30 feet in the air, how high is it after 4 seconds?
Yeah, it's 50 feet.
Yeah, it was 30 feet plus 4 times 5, now it'd be at 50 feet. So then I would put 50 in for Y. You guys kind of with me? I've done way too much. I basically did the problem for you, damn it. You know, I guess-
Not with you.
Oh, then you just use the Pythagorean theorem to get the z.
Yeah. Pythagorean theorem to get the z. Yep. So there are problems just like this in homework, or not just like this, but they had parts of this in it. Okay. So I like some, my picture looks like this too, and a lot of you guys had this picture, but then you had numbers on it, and you weren't sure where the variables were coming from, so you sort of like made them up. But it should just come naturally. What parts of what you're looking at are changing? They need a variable. If the balloon were somehow stationary, then this could have been just a number. And when you do your derivatives, it would have went to 0. We've seen problems like that too. The baseball one, where the one length is 90. And as he's running, that's not changing. That would be weird if the base here suddenly moved just because this guy was running. I'm scared. No, it stays set. Yes? Or like the airplane up in the air, that part stays set. So when I take a derivative, it goes to 0. This one, everything's changing. Damn you, Jeff.
So then.
Say again?
You kind of an ugly answer for this problem.
Yeah, I think it's somewhere around 2, 3, 4, 5 point something. Yeah. Supposed to be about that. Yeah.
I got 4 repeating, or 4.3 repeating.
Sounds right for one version of the test. So yeah, your answer on this problem should be somewhere between 2 and 5 feet per second, somewhere in there, some decimal between like 2.876 or something like that. You guys kind of with me?
So
if
why
you get like 110 feet per second, that ain't happening. It's like, damn kid, or that balloon. Yeah.
So why did you give us the like mine says like 21 feet?
Yeah,
up,
that's
I
where the
think, for
balloon starts. And that's, see the part of the equation that's y?
Yeah.
If the balloon started at whatever,
Uh-huh.
and so many seconds later it went further, now you know this total distance is what goes in for y, because that's the total side of the triangle, right? This is the initial place where the balloon was.
Mm-hmm.
This is later, how much farther up it went.
Oh, so if you.
So if it started at 30, 4 seconds later it would be 50. That's what I would plug in here. So you had an initial position, and then so much time later it's even further up.
Okay.
Okay. Yes?
So you're using your example, you plug in 50 for y.
Yes.
And then 5 for dy dt.
Yes, beautiful. Yes. And then this one works the same way. It was 4 seconds later, 24 feet, so x would be 24. This would be 6. Yeah, okay. I've done enough of that problem for you if you guys can finish it up. Huh? No. Okay. You gotta ask. Alright, anything else from that test? Those are the big ones I wanted to talk about. One little thing that got me worried, well,
Can we review a limit? Oh, that was
is that true?
good. No.
No.
The
What could I put in there to make it almost true?
3/3?
derivative.
Derivative. Why did they say it's not? This is not true. Still, this is not true. Yes, chain rule. The really weird thing about logs is if it has a constant multiplier, it still has a 1/x derivative. Now, why does that make sense? Does anyone remember what the natural log of a times b? What's the property? Natural log of a times x. What's the property?
Natural log of a plus natural log of x.
So if I take the derivative of this is a constant. So of course the derivative will be 1 over x. So that constant multiplier ends up not affecting the derivative at all. It's kind of nifty. You know, like that's one word you could use, Jim. But just be a little. I didn't take off a ton of points on that one, but I definitely took off a point. I think if you did that derivative wrong, it doesn't affect your answer, but it definitely affects the work. Yes.
Isn't it a over x? It's a constant.
Say what?
Is it a over x?
Of course not. Hell no. So, the derivative of the natural log of ax would be 1 over ax times the derivative of the inside. What's the derivative of the inside? That happens no matter what a is, right? As long as it's something that's in the domain of natural log. So what's the derivative of natural log of 7x?
1 over x.
Yes. It's the derivative of natural log of the square root of pi times x. 1 over x. Yes. Doesn't matter what the multiplier is, as long as it's not negative or something that would freak natural log out. Well, even if it's negative, I'm not gonna. Yeah.
So can we go over something like with 4b where like you have to turn the equation into a fraction to be able to use.
Oh, yeah. Okay. Let me think. Yeah, it's hard to come up with another example besides this. Yeah, so if I had this, just to do the first step. This is where I had a lot of people tell me this suddenly equaled x over 7x, which made me think you thought natural log 7x equals 1 over x. Alright, what form is this in? No, because I'm not taking a derivative. I want the limit. What form is this in?
0.
Yeah, 0 times
0.
negative infinity. There it is. Good. I can determine it, but it's negative infinity. Okay. So that piece was negative infinity. Overall, this is indeterminate. Is everybody cool with that?
Mm-hmm.
I really want everybody cool with it. What's 0 times anything? 0. What's anything times infinity? Infinity. In fact, is this ever 0? Does this ever get to 0?
Mm-mm.
No, because it's a limit. It never gets to 0. So it never is 0 times anything. So it all depends on who's getting to the thing faster, which is why L'Hopital's makes complete sense. L'Hopital's all about, holy shit, did you just hear what you just said? It should be dependent on the rates of what each piece is doing. But it only works if I have a ratio. So I can't take a derivative of this thing at all. It doesn't make any sense. I can't do anything with L'Hopital's unless I have indeterminate form and it's a ratio. Yes?
So, but if you plug in 0 for x, then it's natural log of 0.
Which is negative infinity.
Times
Oh.
0.
In the limit.
Oh,
in
yeah,
the limit.
right, okay. Right, okay.
So as I let x go to 0, it never gets there. What do my outputs go to? They approach negative infinity. They get bigger, negative, without bound.
Got it.
Is another way to say negative infinity. How can I make this into a ratio? Yeah.
Oh, okay.
Whenever you move a variable from the top to the bottom or vice versa, its power must change sign. It was happy up top, I moved it down here, now it's upset. There's a really silly way to remember that, right? It's negative on the bottom because it was happy up top. What the shit? So the negative power just reminds me this x was up top. What the shit? It's supposed to flip back up, okay? Human, don't forget that. Why did we do it? Because now L'Hopital comes out of his grave and says, you could do it now. Yes? Oh, hell yeah. You could put 1 over natural log. Do you want to? You could force the natural log to go down. But holy shit. So the other way to do this would be to do this, which you could also look at as that. And then that derivative of the bottom would be much worse than it needs to be. Do you see what I mean? So whenever I have to force something down and make it a negative power, I'm going to take the easier piece. So it doesn't end up with this extra layer of gross derivative. We have the choice. We're the ones with the power.
No, it's way more complicated.
It would work, maybe. All right, anything else? Okay, so don't forget, you can get help with your corrections. Go see the tutors, you come see me. If you think you got your corrections done, you can hand them to me and say, I'm not giving this to you yet. Can you tell me if these look good? And I'll tell you which ones you need to work on. And if I have time, I'll help you with those. Holy shit. I don't think you guys really understand. When I do more than I should. And then I get my students spoiled and you take somebody else on. They don't let me in the correction. I'm like, wow, too damn bad.
That's why you take every class over and over and over again.
Right?
Or like take him for
Three
count
times like
1, then
a
count 2, then count 3, then look your
Oh.
algebra, then differential.
I'm having a discussion with colleagues about if they think that me allowing corrections is sort of like lowering the integrity of the course, and I don't think so. I've kept an eye on that, and I don't think it allows people to pass that really shouldn't. And I understand the concern, which is one reason why a lot of my colleagues don't let people make corrections. One thing is, the people that make really good grades, they worked their asses off to get there. So it kind of seems a little bit like I'm letting these guys catch up, and these guys are like, I can't go anywhere, and these guys, and I can't do shit. So I get that, but I think on the whole, I really feel like most of you guys treat this correctly, which is it's part of the learning experience. Until you take that final exam, your grade should be more dynamic. It should capture what you're currently understanding, and that's my whole philosophy. Is if you can show me you understand something better, then I'll want to give you credit for knowing that. It's the day of the final that you got to show me, and that's it. You can't. I always got a student say, "Can I come to your office and make corrections in the final?" No. Final is appropriate. Anything else? Okay, so put those away. I think I said everything I wanted to say.
How about
What about them? By the way, I've got to go old school because I lost my Apple Pencil.
Oh no!
I was late.
Oh, yeah. Sorry. Anybody else not get their test back? The blue grade's your current grade without homework, and the second one is what it could become if you make corrections and get all the homework turned in.
Would you?
Oh, sorry. Is that everybody?
Do you think you know where you lost it?
No, I know it. It's a bit of a long story, but very quickly. I lost it. I picked up the keyboard. It dropped down. I'm like, oh, good. It bounced. It went under here, and I thought, okay, it's under there. So I moved, went, flashlight, can't find it. I think it bounced up into the bottom of this, onto a ledge. So I got to go back in the room with a screwdriver and unscrew some of the stuff so I can get it.
no.
So that was kind of amazing.
Wait, it's magnetic, isn't it?
Not the type, I got the USB one.
Oh.
Yeah, so it's
I
not
was gonna say,
magnetic,
if it's
but
magnetic,
it was a
you could
perfect
just
bounce.
stick your...
And I just was laughing. My students who were doing group work while I was on the ground, flashing my flashlight underneath, trying to see where it was.
No.
Anyway,
Aw.
I'll be okay. So all that just is to explain why the hell I'm back up here. Like it doesn't matter, Jeff. You don't write good either way. Okay. So, what I want to do today, I want to talk about section 4A and 4.9 and maybe a little bit about chapter 5. You're not going to believe this, I got a handout. So let's talk about 4.8. And I think I want to do this first. Yeah, let's do this first. Does anybody need to borrow a calculator? We're going to do a couple things in the calculator. You're going to need one later for sure. trust you. I'll trust you. You're good? Anybody else?
But it's like that, I'll take that.
Okay. So, does anyone know how to use your calculator to solve a problem like, let's see, Jeff. X squared minus 2x equals sine x. Can you solve this by hand?
You good?
No, you can't because if
Do
you,
it.
if you
This is the
if you
most
take-
boring game show ever. I can solve the problem in 3 years. You guys see how
no matter
whenever you have an x stuck inside of a function, don't we want to kind of like do the opposite of it and free it up? If I do the inverse sine, won't that throw the other side into an inverse sine function? You guys see that? There's no way to get x by itself, by hand, easily. Yes.
Isn't X just 0?
Yes. So that was my next thing was, can you just plug numbers in and see what works? Yeah.
I was saying you could, because technically you can, it won't be pretty.
So with this
That's
one,
what
you
I
can
was
say
thinking.
x is 0 because you can see 0 minus 0 equals 0.
Yeah, I was just joking.
So what about this one?
You know, watch
What's cosine of 1?
0.
Hell no, guys. Hell no.
Should be.
Oh, wait, here's.
Cosine of pi over 2 is 0. Pi over 2 squared minus 2 times pi over 2 is not 0. Yeah? Could you guys, use intermediate value here to plug an x in where one side is lower than the other, plug an x in where one side is higher than the other, since they're both continuous, that must mean the answer is between those two. Yeah, you could, okay. So let's use the calculator instead. I'm gonna use the calculator first, because I wanna remind you guys that this calculator is able to do this. And then we're gonna actually get into the freaking math behind what the calculator does to do it. It's not freaking magic, we didn't put a little put the magic module in the calculator. Right? Like, I'm sorry. It's like Thanos and his, put the stone in, now I'm able to do this shit. No. It doesn't work that way, you don't have to kill Vision to get the thing, don't worry. Get people sad. So, what I'm gonna do is I'm gonna hit y equals. Anything that's in y equals I'm gonna clear, because I want all that shit out the way. I got my own stuff to worry about. You with me? Everybody's all clear, y equals, everybody goes. Let me know the minute weird things happen. Okay, so we already got y's here, yes?
Mhm.
Nobody has an r here, yes? Okay. So y, you could have an r there, by the way, just to let you know. So y equals, let's do one side of this, x squared minus 2x. And then, you're never gonna believe this, but I'm gonna put cosine x on the other side. And while I'm thinking about it, what do you guys think I should be in? Radians. Before I forget, real quick, there was an earlier problem of 2 degrees per minute or whatever. I don't know if you remember. So the answer had a pi in it. I think you and Natalie were talking about it.
Oh, yeah.
That's got to be in radians because it's not inside of a trig function. So anytime an angle is not inside of a trig function, it must be in radians. If I ask you right now, what's the sine of a right angle? What is it? Yep, sine of a right angle.
1.
1. Is that even in degrees? Did I just say something in degrees? I just said I said words. Sine of a right angle. So I could put a freaking phrase inside of a sine function. All I need to know is what angle are you talking. I can use degrees, radians, words, pictures, whatever the shit. When an angle is on its own, not inside of a trig function, it's got to have physical meaning already by itself. So therefore it has to be in radians. So isn't x an angle?
Mhm.
And aren't these x's out by themselves? So it better be in freaking radians. So let's see. Am I in radians? No. Okay, now I am. Everything's good. Go back to y equals, okay. Make sure you're in radians. Now if I graph this, let me see. Good, okay.
Oh, mine worked.
Oh yeah, it's fine, because we all have different, I'm using a calculator from the bag. I have no idea what student did what to this poor little calculator. So I'm gonna quit. My window's all freaky.
Oh, that's why. Mine's
Yes.
like -50.
So what I'm gonna do is I'm gonna hit zoom 6 to get a standard window. So there's my parabola. And there goes my cosine, no kidding. Oh, he's so cute. Okay. Let me do one little thing. Everybody do this with me. Do window, do y max, y min -3, y max 3. Y min -3, y max 3. Make sure you hit the negative, not the minus key. That actually rhymed. Yeah.
What's that invalid dimensions?
Oh, hit second y equals number 4. Enter. Does it say plots off?
Yeah.
Did it say done?
Yep.
Now hit zoom 6. I'm sorry. Well, whatever you gotta do. Get to the graph. It should be able to graph it now. So for the rest of us, it should look a little bit better. Did I actually change the window? I guess I did. Yes, I did. Okay. Can you guys see how many answers there are to this equation?
2.
2. There's one there and one there. So what if my problem specifically said you gotta find the positive answer? I wanna find the positive answer. I want to make this calculator do it. This calculator costs enough money. And it's got graphing in the title of it. The entire top row of this calculator is devoted to buttons that do graphical calculations. Yes? This whole first row is graphing shit. And look, it's got a whole calculate button. Sorry, people in the next room. I wish that would be so cool, but you got no. All right. Has anyone ever done this before? I'm sure some of you have. The intersection of two functions.
Yeah, you taught it
So,
to us, I think, in pre-calc.
True. So if you took me, we did it, but you never know. So I hit second calc, because I want to calculate something graphically. And which one of those seems like it's doing what I need it to do?
Intersect.
Holy shit. Look at this, by the way, number 6. If you guys just read your calculator manual, it would have done derivatives for you. Oh, too bad. So number 7, you should keep track of that one, because that one's going to be neat. But I'm going to show you that.
Integrals. Ugh.
Dudular. All right, now I hit enter. And it's got a little cursor that opens up, right? A little cursor. Now notice this. It says, what's the first curve? Right? Okay.
First curve is the first function. Put in.
So watch this. I want to show you something. Pull your cursor over to there just so you can see it a little better. Now if you hit enter, watch what your cursor does. It bounced to the second curve, right? And what's the question now?
What's the second one?
Second curve. So then I'm going to hit enter because I'm on the second curve. And now the question is guess. So what's my guess for the answer is right there. Enter. So then it gets this answer.
Hey. Oh, I got the same answer.
No way. Okay. It would be really, really weird if you got a very different answer.
I was glad my thing's programmed right.
So if I wanted to do something, is everybody kind of with me? Does that sound familiar? If you didn't know that your calculator could do this, I just showed you how to solve every equation in the universe. You take one side, put it into y1, take the other side, put it into y2, graph it, find where they meet. You've solved the frickin' equation. What is the answer to the equation? What is the answer to that equation?
1.8507174.
That's it. This piece doesn't matter worth shit. This is just a number that both sides happen to equal. The answer to that equation is an x value. Okay, I like it. I like it. Now, just to make this a little more what we're going to do today, couldn't I have subtracted cosine x over?
And then factored out.
Right?
Maybe.
No, I can't factor it. Is this quadratic? This is Definitely
No.
not quadratic.
Because you have the cosine x.
Because this guy, yes. This is not a constant. It's some function of x, so it's not quadratic. Okay, but this would look very different in the calculator. What I would do now is I would have one function. And what am I trying to make the function do? Equals 0. Sorry, I'll get the same answer, but kind of in a very different format. So like, if I put x squared, you can do it, Jeff. Minus 2x minus cosine x, and hit graph. Now my function is going to look very different. In fact, it's not going to look that much. There it is. Okay. That looks basically quadratic, yeah? Because the cosine x goes between
Negative pi over
negative
2.
1 and 1, so it's really not going to affect the outputs. Do you guys see how this, I don't know if you guys can see the curvature of this is a little off. I don't know if you guys can really see that, but the cosine's not going to make that big of an effect. If I find that intercept, how will that relate to what we just did earlier?
Should be the same.
It'll be the same answer because I'm answering the same equation, just rearranged. So of course the math is going to come out the same. The math doesn't give a shit where you put the cosine. So now what am I going to do though if I want to find this? Second calc, I want to find the 0. Now here's where things get really interesting. The questions it asks, it doesn't need second curve, first curve, because now I've just got one curve. It wants to know where to search in. What's the left bound? So what I normally tell students is put your cursor on the answer. It puts the cursor on the answer. Hit the left button like 3 times. That's definitely to the left of the answer now, yes?
Mm-hmm.
Enter. Go back to the answer. Now the question is right bound. Hit the right arrow 3 times. That's definitely to the right of the answer. And now the question is guess, so I put the cursor back as close as I can get. It's going to search in here. And then incredibly enough, it gets the exact same answer. Okay, so what we're going to focus on, hopefully that's familiar. If you never did the finding the 2 curves, hopefully more of you did the just finding the x-intercept. Okay, I like it. Okay, so has anyone ever wondered what the shit this is doing?
No, it's just
When you, and some of you guys are like, not even right now, man. If I say no, can we just skip this section? No. So, if you're not curious at all, I have enough curiosity to handle that. I could be curious for you. Hopefully some of you guys are like, yeah, I'd like to know. I think I told you I wrote to TI about some other things and they thought I was a spy from HP.
They
like,
did.
I can't tell you shit, man. I don't know who you work for. I just gotta find that email. I should print it out and share it. I just want to know how they modified something. And like, what are you trying to get? What are you trying to do? Oh. Okay, sorry.
Yeah, I was like,
I would have sold it to HP, but I mean, I wasn't working for HP yet. Okay. So, we want to develop a process that if I'm given a function equal to 0, I could then discover its x-intercept, basically. If I'm given a function, I want to find its x-intercept. Or one of them if it's got several, right? Okay, so let's say I'm given a function. And let's say the function looks like, wee-haw, so it's definitely got an x-intercept right here, yes? Let's say I want this one, not that one. You couldn't even see that one for a second, so this is fine. Okay. I want that x-intercept. And let's say, okay, I know this. Couldn't I take a guess as to what that is? I can take a guess, correct? I can say like what'd you say? Well, I'm sorry. I thought it came from you. You had your mouth open. I thought it came from you. 1.7, 1.8, something like that. Yeah. So I'm gonna call our guess x1, and we're almost definitely gonna be off. Our guess is not gonna be perfect, but it's gonna be close. I mean, we can see the damn thing. It's gonna be around there. You with me? Now this process is really freaking cool as shit. Let's see if you guys are like, if you say that, I really don't trust you. But if I guess, let me make this a little more extreme, okay? Let's say that I really suck at guessing, and I'm going to guess this, just to make this a little bit easier to see what's happening. So my guess is that. So my output is here, yes? For that guess. If I find the tangent line to that curve that goes through that point, then that would, now that's a little too perfect, but oh, I love it when I'm trying to draw my own stuff. Let me try this again. I made that just a little too perfect. So what does it look like? This, like that. Yes, Jeff. It's got an X1 here, and then it's got this, and it's got, yeah. So let's be a little less specific. Okay. That's a little worse now, Jeff, but this will be fine. So if I get the tangent function, this, if I've picked well enough, will be closer to the actual answer. Do you all agree from my picture that this is a little bit longer than that?
Mm-hmm.
Do you all agree my guess was actually kind of sucky? Okay. So this would be x2. And then the whole process happens again. Isn't this f of x2? So this was f of x1. I made a tangent line. I really, right now, just want you to get the concept of it. We're going to get the specifics in a minute, the nuts and bolts. I just want the concept to be what you're getting right now. And again, I've done a horrible job, but just pretend like it's here. Okay. And when I do this tangent line, this would be x3. And then I do it again. Here's the point. I get a tangent line. And this will be x4. Now I'm getting really close to it. Every time I do it, I get a little bit closer. Yes? Get a little closer. Now watch. Does everybody kind of get the idea? There's a lot of math behind what I just said. We got to construct a tangent line. We got to find its x-intercept. We got to use that into the next thing. We got to find the new tangent line. Holy shit. Yes?
So if your original guess was just a little bit worse,
Yes, good.
If it was worse, then you would end up going the wrong way.
Perfect. Which explains why the calculator asks the first two things it does. So if I draw my graph again, if my guess would have been here, I'm sorry, that would be even worse. So here's the intercept. If my guess would have been here, my tangent line would have taken me here, yes? What was the first two things the calculator wanted from me when I was trying to get it to get the intercept, the x-intercept?
The curves.
Nope, that was for when I had two curves. When I had one function, I want the intercept.
Left and right
Left
bound.
bound, right bound. So I would tell it here and here. So that if for some reason its program gave it a guess of this, it would go, well, that's obviously wrong. It would restrict its first guess to be in here. Does that make sense? Yeah. Now again, if I put my left bound, my right bound too big, the program's not going to survive that shit. As a human, I got to do my part. So you're right. The worse your first guess is, it can either make it take longer to get close enough, or it could actually make you go completely to infinity, possibly. You go over here, and then you make a tangent line, you go over there, you make a tangent line, you go way over there, you're like, holy shit. And that's when it would go, overflow, leave me alone. You guys kind of get the idea. Okay. Take that as a no. Shoot. Let's see. So the idea, again, we just focus on one thing. If I guess here, and I make a tangent line here, this is horrible, but too bad, then my next guess is a little closer. What if I guessed over here? Then my tangent line would still take me over here, and my next guess would be a little closer. So this is what's going to be called an iterative process. Anybody know what iterative means?
You
It's like
repeat the same thing
repeating.
over and over.
Repeat the same thing, just with new inputs each time. So what we're gonna do is we're gonna develop a process, and then eventually we would just put something in our calculator and hit enter, because we just wanted to keep doing the same damn thing over and enter, until we see our number sort of not changing anymore. So it's just doing this, and then this, and then this, and then this, enter. It's like, okay, dude. And that's basically what it's doing internally. It's doing that. Okay. So, Jeff, why are you yelling? No, be quiet. This is my f of x. This is my guess. This is my f of x1. I need to make a tangent line, correct? Yes?
How do you know which bounds, like how the bounds should be?
How do I, sorry?
How do you know which bounds are like?
No. If we do this, what's it? No, I'm good. Thank you, though. I had to pair it and all that kind of business on it. Don't worry about it. I don't even know my charges on the poor little dude. I kind of gave up on him after I lost my pencil. I appreciate that, though. Okay. Hit me again.
I don't know what
Oh. If we're doing this ourselves, so we're the calculator, we just have to have a good guess. And the minute we do our first couple of steps, we'll know if our guess is really bad. Does that make sense? I'll hit enter, and then it goes from 3 to 10. Enter 1,000,000. Enter 2 billion. Oh, well, shit.
So
My guess was bad.
So this has to be like graphically, right? Like you can't just get off.
Yes, the calculator is dumb, so it needs some help, right? That's why we give it bounds, because it's not human, it's not AI, and even AI isn't AI yet, right? Thank God. Okay.
So now,
Yeah, exactly. Not yet. Do you want to play a game? Okay. So let me talk about the math a little bit here. So how do I construct? All I want to do at first is construct a tangent line, because if I get the intercept of the tangent line, that would be, as long as my first guess was good, that will be a better guess. And then I'll just kind of do it all over again. And then the x3 will be a little bit better. Beep, 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 beep. Okay. So let me kind of list what we know. We know that I got x1, f of x1. That's all we know. How do I construct a tangent line? What do I have to know?
A point
Point, check.
and the slope.
Slope! No check yet. How do I get the slope?
The
So I don't have 2 points really, because I need this to be able to go. I just have the 1 point. So of course we're going to use derivative. So f prime of x. In fact, to be really specific, my slope will be f prime at x1 originally. Yes? Let me stop for a minute. Or a moment. I love it, guys. What we're about to do is we're going to derive an algorithm, which really is just another word for, in this case, a formula that's going to get repeatedly used. So it's a little algorithm that we throw a number into, and it kind of like is a washing machine. Boom, 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 and then out comes the answer. So let's put this together. I got a point, and I got the slope. How do I make the line? Yeah, y minus
Y1
f of x1 equals f prime of x1 times x minus, no, you can do it, x1. Isn't that basically the linear approximation formula?
Mm-hmm.
Because all the linear approximation formulas are freaking tangent line formula, yes? Okay. So we just constructed the tangent line to a function with an initial guess of x1. What did I want to find from that? Now that we have the tangent line, what do I want to find from it? It's,
derivative.
no, it's x-intercept, yes. I'm sorry, I heard several answers. It was like, which one? How do I find the x-intercept of any function in the universe?
Set it equal to
Set all the other letters equal to 0. So in this case, I just said y equal to 0. I really want you guys to really, every step we're taking is nothing new. Nothing we're doing is new. Not a damn thing is new. We're just using it in a different way. We've made tangent lines before. That's y minus y1 equals mx minus x1. Ooh. Literally x1. Look at that shit. We found x-intercepts before. So what do I get? What am I going to try to solve for when I make y 0? If you want to find the x-intercept, you make y 0 and you solve for x. Good. So make y 0, I get this. How do I solve for x?
make x.
Instead of distributing, I can divide. Yes?
And you get -1.
Die. So let me pull this over here just because.
Wait.
So I divide it by f prime, and I put that there, right? And then what's one last step to get x by itself? One last step to get x by itself?
Put everything
No?
with x.
Just add x1. That's all I wanted to hear. That little dude, let me write him again. Okay, let me write him again. Because he got a little smushed. Poor little guy got a little smushed. Poor little guy. He didn't want to exist. Because existence is pain. Okay. So that's him written again. Again, this is something students really, I wish, got more practice with this kind of thing. Does this look like anything you would ever expect to come out of anything?
No.
Ain't no way. But didn't this come from us following procedures we've done a billion times? Have you found a lot of x-intercepts in your time? If you haven't, what the hell are you doing here? You should have found a lot of x-intercepts in your time, yes? And what we did was exactly what we always did. Have you found a lot of tangent lines in this class? You're like, yeah, I wanted to talk to you about that.
Tried the phone.
Yes, at least I asked you to. So we got, all right, that's all I'm going to say. That's what this came from. Don't freak out about what it is. Like, where did that come from? We know exactly where it came from. So what do we call this then? This specifically, what am I going to call this? Let's see if anybody was paying attention. That's going to be our x2. That's going to be our x2. So I plug x1 into this process, it'll spit out our next guess. How do I get x3?
Do it again.
X2.
Plug x2 into the process, and it'll spit out x3. How do I get x4?
Plug in x.
Plug x4. All right, so how do I get x of n plus 1?
You plug in
X of n.
X of n.
x of n.
All right, so let's try. By the way, the whole point of this is not to create something that we don't need a calculator for. The whole point of this is this would be a subroutine. This would be like a little program in the calculator that it would feed shit to, calculate what it needs so it can get what the next guess, and then it would feed that back in, get the next guess. So we are going to use the hell of our calculator on several parts of this. So let's do an example. Crazy enough, the example I want to do, I don't know what I've done with it. There it is this. So didn't this come from this? Could you guys graph a rough sketch of x squared minus 2x? Can anyone tell me any damn thing about x squared minus 2x?
It's a parabola,
It's a parabola.
and it's
Intercepts are, x-intercepts are 0 and 2. You guys see that? Because you can factor it x times x minus 2. And it opens up. That's basically all I know. All I need to know for a rough sketch, yes? Okay. So I know it goes 0 and 2. I know it opens up. Okay. That's a wonderful rough sketch. I could plug a 1 in. What do you want to plug a 1 in? When I plug a 1 in, what do I get?
1 squared.
Yeah. 1 minus 2. Negative 1. Yes? Is that cool? So it gives me a little scale here. Okay. We haven't done anything amazing. What about cosine x? Where does cosine x start? At 0, it's at 1. When does it go to 0?
At pi over 2.
What is pi over 2 roughly? What is pi
90.
roughly? 3. I love it. What's 3 divided by 2? 1.5. 1.5 is right here, yes? So doesn't cosine go like this, and then it turns? Then can't I get a decent first guess from that rough-ass sketch? There you go. If you took me for pre-calculus, and I told you, in pre-calculus, I actually told you, hey guys, this is graphing hell, by the way. I don't know if you guys remember that. If you took me, yeah, some of you guys are like, yeah, Jeff, yeah, and you lived up to it. Because that needs to be stupid easy. That's just a rough sketch. That's nowhere near what I asked for you from pre-calc. But since you went through everything you did in pre-calc, you should be able to create that really easily. What would be a good guess then? It's between 1.5 and 2. So I don't want somebody to just kind of read off the answer from earlier. My guess would be no. But what's a good guess? 1.7. 5, sure. So we'll guess 1.75. So now we have the process. How do I get x2? I do this. We'll do a couple of these and then I'll show you the ultimate shortcut. So I need, sorry? Yeah, Jeff, just hit the button, man. I love it. So 1.75 minus f of 1.75 divided by f prime of 1.75. Of course, what part of this have we not done yet? Yeah, so what's f prime? What is f, by the way? What is it?
X squared plus x squared minus 2.
It's the thing that equals 0, exactly. So if it gave you this problem, you have to subtract cosine because f is the function that's equal to 0. So if it's not equal to 0 yet, you better pull that sucker over so you know what the hell f is. What the f? And then, so what is f prime?
2x minus 2 plus sign.
I like it. So there's my f prime. So now, can somebody help me out? This is the one I'm going to make you do fully. Can you just please plug shit in your calculator? In fact, let me show you some. You guys ready? This is the ultimate. Okay. This will kind of get us right. Oh, this is beautiful. Okay. I'm going to show you one level of goodness, and then I'll show you the ultimate level of goodness. Okay. What'd you do in class today? Ultimate level of goodness. So, what is the value we're working with? 1.75. So everybody put 1.75. Really cool button down here, store. Or store in X. Enter. Yes, sir.
Side question. Is there a way to clear what you have stored for X?
You don't have to. When you store anything, it overwrites what's in there. Yeah. If you have something in there you want to keep, then you can use a different variable. Is that all right, David? I don't want to take away if you got your favorite number stored in X.
No. I tried to use X other times and I've gotten like weird numbers, so I thought maybe I had something stored in there that I didn't want.
Oh. Now it should be, now everybody, if you've done this, hit X button. Enter. So it's 1.75. Okay. Now,
How'd you do the arrow?
sorry?
The arrow in between the 1.7.
Store.
Store.
Yeah, when I teach statistics, I definitely show students this because they have some long ass formulas. Now watch what you're gonna do. What do I want to do here? Don't I want to do,
X over.
yeah, I want to do 1.7. Let me just write, I want to do this divided by this, evaluated at 1.75, yes? I really want you with me. I want to do 1.75. I want to do this minus, let me see if you guys are cool with this. You ready? I'm just gonna, you ready? I don't know if you're ready. X squared minus 2x minus cosine x. Why will that give me what I need? Because x is 1.75. Divided by what? 2x minus 2 plus sin x. No joke. As long as you did parentheses for the top, yes? So you have 2 there because one's for the cosine and one's for the top. Time, what do I have? What does that say?
It's a multiply.
Okay, this is why it's a good idea to look back through. Delete. Divided by parentheses, 2x minus 2 plus sine x. So now it's got the top, it's got the bottom. You guys kind of with me? So let's see if we all get the same answer. It's going to be exciting. Who wrote down the answer from earlier when we did it in the calculator? Did anybody do that? If not, then I'll
no,
do that for
but
all of us.
That's
I,
what it was. It was that.
It's close to that.
it was 1.85071 something.
I could store that in there and then hit enter. Let me show you the ultimate goodness. That's pretty good. Did anybody not know about that? That you can use store in a variable and then put an entire just function in? Isn't that kind of cool? Don't you wish you knew that in pre-calc? Now, here's the ultimate goodness. Don't you wish? I need you to understand. If I hit enter right now, I'm going to get the same answer. Because x is still freaking 1 point. I'd have to manually change x's value and then go back up and highlight this and hit enter. Don't you wish I could make it so it just hit enter, 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 and it just keeps putting the new number in automatically? So there's an ultimate best memory location on your calculator, and it's called, careful, I'll say this because people get really weird. ANS. Above your negative key, yes? So watch this. You ready? You guys aren't ready. Everybody hit 1.75 again. This is the magic. The ANS, the answer key, always has the last number that showed up in its memory. You guys with me? So the minute I do shit to it, it changes because now the last number that showed up is the new number. So if I build my algorithm with answer instead of x, so instead of x, I'm going to put answer. Answer minus parenthesis, just put all this answer squared, minus 2 times answer. This is going to be exciting. Minus cosine of answer, parenthesis, divided by c. I'm just replacing x with answer, yes? It's effectively doing the same thing x did. It just has something it does even better. Where'd I go? Divided by parenthesis, 2 answer minus 2 plus sine answer. If I hit this once, I should get the same answer we just got, the 1.85. Please, dear God, tell me I put stuff in correctly. Did I put stuff in correctly? Yes. If I hit enter again, it will now redo this. But what is ANS now?
That.
This number. Isn't that what the whole algorithm needs? It needs the new guess plugged in, and then it needs that new guess plugged in, and then it needs that. So if I just hit enter until the numbers stop changing, did the numbers change a little bit?
Yeah.
Are they changing a lot? Well, they still changed, yes?
Yeah.
They did it one more time. Did they change? Nope. So we're there. We're as good, as close as we can get with the resolution of the numbers on the screen of the calculator. And I don't know if nobody wrote that number down, did you guys? I love you guys so much, little tear. It should be that, yeah. So let me give you this handout. On the other side is something we're gonna do in a bit, probably after the break.
1.85071.
07.
077174.
Oh, beautiful. Okay. It's even more precise.
I'll tell you.
Yeah.
Oh, infinity. You have to remember always plus C.
So guys,
Yeah.
I give you an example here. Now obviously here, this is not hand drawn. I don't know if you can tell. Normally I draw just about this good. But
Sure.
part of what this would require is for you to draw by hand a rough sketch, and then you get a decent little. Most of the functions we're going to work with are going to be well behaved. Does anyone feel comfortable to tell me what that means? I've used that phrase a couple times. Well behaved. Well behaved. What makes a function well behaved?
Stays the same.
Stay the same would make it really well behaved. That is a very well behaved.
Doesn't do it.
If this is your kid, I'm worried about your kid, by the way. I mean, your kid should be like, wow, and that would not be well behaved, right? So a function that's not well behaved is changing very quickly. It's got rapid movements. It's like, so this is a well behaved
changing
function.
slow.
Ooh, look at that function, so well behaved. This one's like, so if I had a function like this is a part of what I'm working with, wouldn't my guess have to be stupid close, or else my tangent lines go insane very quickly? You guys kind of with me? So most of the ones we're going to work with, in fact, all the ones I think you're going to work with are going to be well behaved. So it's what's called robust against a bad guess. Does this make sense? Everybody know what the word robust means? You can handle something better if you're robust. If your house is robust against a storm, it can stay standing through a bad storm. Yes? And if it isn't, okay. Okay. So I just kind of spell out, yeah, good. I did give you like the format. So this is a good little thing to have next to you while you're doing section 4A. Okay. So, let us take a break. Come back at 5 after. Take a little time break. Little time break. I did.
Oh, duh. That's why Uncle Jason. We're going over to mine.
Are you gonna be something?
Huh?
Are you gonna be something for Halloween?
He actually really.
I was planning on that.
he does.
I'm really worried I'm not
Yeah.
going to be here tomorrow.
No, like Halloween.
Because right now I'm on some big old painkillers because this thing is insane.
You always watch that.
Yeah, and tomorrow
Oh,
it's
now
more
I
than
see.
likely
Oh,
going to
it's
close
his
up.
favorite movie ever.
Now I
So,
see it.
we'll see.
And it's so funny.
It kinda sucks, cause I have
Literally tell
anyway, so
that it's
I was gonna be like a steampunk
Chocolate.
scientist, but we'll see.
Steampunk scientist?
Yeah,
But like, this X is.
I really like the costume, I don't know.
my dad was really heavily into musicals, and one of his like well, can't say all time favorite because he has two, is Phantom of the Opera.
Yes?
And
The
so he went,
Phantom of the
and so he went as Phantom one time when he was, but it was kind of bad because at that time he was working at the bank, and the Phantom costume has a mask.
True. Which is, yes.
So, but it was interesting because he didn't have to buy the tuxedo. He already had it because he worked at the bank.
Oh,
And then
if you work in a bank, you have to have a tuxedo?
for when he worked though,
If I were x equals 2, would it just be the plus or minus the square root of 2?
Sure.
So, okay, we're just gonna.
But this is an example of a problem. You can get the answer easily, but I just want to show the process.
Yeah.
So very often when we learn a process, we start, the very first example we have is one we could do a different way. If the process doesn't give the right answer, then we have to throw it out or something went wrong, because we already know what the answer is supposed to be. And then we followed up with a funky thing that we can't get directly. Because now we've bought into the process. The answer I got is the square root of 2, right? Well, we got it without taking a square root. Do you see what I mean? Yeah. So it's just to help people buy into it. Okay, I got the answer I would have gotten anyway. And then the next example is like, I don't have another way to get the answer, so now I buy into this process. Cool. All right, guys. Everybody.
Go home.
I mean, it's college, it's always an option. So, thankfully these guys aren't out there making a lot of noise yet.
okay.
4-8, hopefully you don't think it's that bad. 4-8's really not that bad. Most of the badness was just the derivation. You never have to derive it yourself. I'm not gonna make you memorize the Newton's method, okay? In fact, I didn't even give Newton credit. He's somewhere rolling over his grave. I'm so sorry, Newton. You guys have heard about Newton? He's one of the fathers of calculus, and you're all like, no, Jeff, we don't care. Okay. So that was Newton's method. That's what Newton came up with way back in the day, way before we had anything approximating calculus. Huh? Oh, yeah. So, let me think. What we're about to get into, just to let you guys know, if you have any trouble with derivatives, you've got to firm that up, because what we're about to get into is antiderivatives, which is sort of like, if I ask you this question, what is the inverse sign of 1/2? First off, you have to remember what the hell that means, right? What that's really asking you is sine of what angle is 1/2. If you don't know your trig values, there ain't no way in hell you're gonna do anti-trig. The inverse trig, are you guys with me? If you don't know the original, you can't answer an inverse question. So, the process we're about to get into is the inverse of derivative process. If you don't know your derivatives, there ain't no way you're gonna think backwards. So let me ask you this. If I tell you the derivative of something is 2x, what must have been the original function? Now let's see what. I know some of you guys know the magic thing that drives calculus students crazy. The second half of calculus. Calculus? Sure, Jeff. The second half of calculus. Where your toes
Wait,
slow.
is it a disease now?
It's a disease. Calculus is actually a condition of the teeth. You can look that up.
Surprised, not even a
This is 4-9?
If f of x, yes, 4-9. If f of x is x squared plus 11, what's f prime?
X squared, negative x squared. No, negative 2x. Oh my god.
If f of x was x squared minus 137.2, what is f prime? 2x. You guys got it with me? So if f of x is x squared plus any constant, what's f prime?
2x plus a constant.
No.
No.
Derivative of any constant is 0.
0.
So when we're thinking about antiderivatives, we have lost information. If somebody took a derivative of something, if there was a constant there, it is gone. And if we're trying to work backwards, I don't know what it was. So what do we do to cover our ass is we just say plus c. And if they give a shit about it, you say, you took a derivative, man, I have no idea. Plus something. You guys kind of with me? Some other jerk took the derivative and made the c go away. So yes, some of you guys know all too well that there are tests and quizzes where you'll get back and you'll lose a lot of points because you forgot to put plus c.
Yeah.
It is
Yep.
not correct if you don't. So let me ask you this. Can you guys draw a line that has a slope of 2? I'm almost certain you're all going to do the same thing. But draw a line that has a slope of 2. Go. And I don't mean, it's got a slope of 2. No. Draw a line that's got a slope of 2. Go. A line that has a slope of 2. I'm not sure why you're doing this.
They have multiple slopes of 2.
Well, just draw a line that has a slope of 2 on your paper. I'm sorry, everybody's. I don't know what's happening. Has everybody done this?
Up 2 over 1.
Up 2.
Yeah. Why can't you? Now I like it. David, I like that you have a little, or you're highlighting an issue. Did I tell you where to start? Could you start at 0?
Yeah.
And then I go up 2 over 1. Yes. Yeah. Couldn't I have started at 2?
Mm-hmm.
Up 2 over 1. Yeah. They're all going to be parallel because they all have the same slope, correct? So x squared plus c is a parabola that's been moved up or down, correct? Doesn't have the same damn slope at every single x value. It's got the same slope. I don't care if I go, oh, no, it's still flat at 0, dude. Oh, it's still flat at 0. As long as I don't do this, it's got the exact same damn slope. You guys kind of with me? So again, if all I know is the slope, if I'm trying to work backward to what the function was, which is just what that was. I gave you the slope of 2 and I asked you to graph the function. I'm thankful some of you guys are like, where do you want me to start? I didn't tell you the value of c. So there were infinite number of possible answers. Yes?
Now I see like the true meaning behind the tangent line parallel question on test 2, I think. Where it's like the same slope. Just
Oh, sure.
different
Okay.
constant.
Sort of, I guess.
Yeah.
This has an idea of the same slope.
Yeah.
Okay.
And like
All right. Nothing that will help. Let me say it like that. So you can see if the worse you know, the worse memorized your derivative rules are, the harder time you're going to have with this. So for example, if I told you f prime of x is cosecant squared x, what was f? Kick ass.
Yeah.
So if you put cotangent, that's wrong, because what's the derivative of cotangent? Negative cosecant. So what must there have been? Since there's no negative here, there must have been a negative that would have killed it, yes? Why is this still wrong?
Because it does not have plus c.
There you go. Said in the appropriate tone. Okay. Sorry?
Yeah.
What's, oh, this stuff? Okay, sorry. So that was just the idea of it doesn't matter what this constant was, after a derivative it's gone. Alright, I like it, yes,
how many points would you take it off for
so many.
the net, not the C,
The most
the
important.
negative sign?
Oh, for the negative sign?
Yeah.
Well, that's kind of big. I don't know, it depends. I take off 20% of the points. Maybe, I don't know. So what if G prime was, let's say 4 sine 2x. Let me help you guys out. Forget about the 4. Forget about the 2x. It's sine, correct?
Mm-hmm.
Where would it have come from?
Negative cosine.
Negative cosine, because the cosine would be negative sine, correct? The derivative? So we know there should have been a negative cosine. I'm going to put a negative, I'm going to leave room, and I'm going to put a cosine. When I take a derivative, does the inside of a function change? No, because that's chain rule. Chain rule says you get your term next, correct? So this inside would still be 2x, correct?
Mm-hmm.
So we're not done, because what is this guy's derivative?
X squared.
What is this guy's derivative?
4 sine.
No, it isn't. What is this guy's derivative?
Negative.
There's a negative.
Sine.
Okay, let me see. What is the derivative of negative cosine 2x plus c? What's the derivative? Sine 2x times 2. That goes
Plus
away,
c.
yes? No,
Oh,
derivative.
No derivative.
Yes.
Oh my god.
Okay.
I'm
What's
trying to
the-
put plus
is everybody with me?
something like that.
If I have this, what is its derivative? The derivative of cosine is negative sine, so the negatives cancel.
Mhm.
Inside's still there, and then chain rule says the inside gets a term. I just put it out front. Okay, that's all. I hope we're all there. I get to put the chain rule thing out front as I go instead of rewriting the whole damn line. Okay. What's supposed to be here? What must have been here already then?
A 2.
Done. Yeah, maybe. So you start to see. Now this should make sense. Were derivatives always straightforward? Were they always straightforward? No. Now, if any of you guys have ever done any integration, antidifferentiation, compared to that, they're much more straightforward. But were derivatives always straightforward? Couldn't I have multiple chain rules? Would you say that's straightforward? Couldn't I have a chain rule that has a quotient rule inside of it, that has its own chain rules inside of it? Would you say that that's straightforward? No. You could say it's straightforward, just a lot of work, but still, there's a lot of steps. You guys agree with me? I need this to make sense. So, undoing differentiation, we should expect it to be a little worse. Basically, across the board. Anything differentiation has that's complicated, undoing that shit is going to be a little more complicated. You guys kind of with me? And I'm not saying this to make you go, oh, this guy's making me feel great. I just want you to realize you have to know your basic derivatives, because what you should be learning is all the weird shit you have to do to counteract product rule, chain rule, when we have to start thinking about those backwards. What we just did was a very basic undoing of a chain rule, but do you all agree it was definitely a little worse than just make straight up chain rule? Because you gotta think backwards. You gotta think what should have been there to make this happen. Okay. Again, I'm not saying this to make you scared or some shit. I'm just saying this is the way it is. Okay. So, turn your Newton's method paper over. And if you threw it away because you hated it, then I have more copies, but I'm not going to give you any. You're going to learn less. Okay. No, I don't think anybody threw it away. But if you did, too damn bad. First two questions, do it real quick. That's just derivative, right? That's straight up derivative. That's all I want from you is a derivative. Yes?
Would all the integration be like just undoing? Because like, is there a better way for it's complicated?
Hell yeah. So, remember when we had limit definition derivative? Didn't we develop shortcuts so we didn't have to do that for everything? Then what if I had 2x plus 7 to the 80th power? One way we could do that is to multiply that out. 80 times 4, falling 80 times. You with me? That is one way we could do that, yes? Didn't we develop a differentiation method that made that easier? Okay. So we're learning the basics of anti-differentiation. We will then build shortcuts and procedures that will make it easier the more complicated the thing is. Yeah, good, okay. So what is the derivative of a natural log of x plus 2?
1 over x plus 2.
1 over x plus 2, because chain rule doesn't really apply because the derivative is just 1. I like it. So what would the antiderivative of 1 over x plus 2 be?
Natural log of x plus 2. Plus c.
There you go. I knew you did it. Have you guys done this one yet?
2x.
Yeah, so the 2,
4x.
2 comes down, right? Let's just do it step by step.
4x times x squared plus
Do the first, times the derivative of the inside, which is
2x.
2x, and now we'll catch up with Sarah, and we'll say this is 4x
Times
x squared plus 3. Okay. So now do this one.
Natural log of x minus c. Plus c. I'm just gonna start
You
throwing
guys see
plus
that?
c's everywhere.
The antiderivative of this, of course it's ln x minus 3.
Plus c.
Now to be really, really honest, there's one thing that's not quite right here. Let's see if you guys remember. We talked about this with ln before. What is the domain of this? What's the only thing that this is missing?
X cannot equal 3.
And what's the domain of this? X has to be greater than 3. Do those domains match? Does anyone remember what I should put here?
The absolute value.
You guys remember that? Now that has to show up, because now we're going backwards. To cover my ass, I better put absolute value. If I plug a 2 into this function, does it freak out?
No.
Not a damn bit. Unfortunately, we're all cool with negatives, especially banks. You guys with me? You guys with me? If I plug a 2 in before I put the absolute values, would this guy freak out? Would this guy freak out if I plug a 2 in him? He would freak out very much. In fact, I doubt any of you have talked about how that leads to complex numbers. For right now, we'll just say you can't do it, okay? So I have to put the absolute value because this function came from this function. This function came from that function. They should have the same domain. Or else it just doesn't make any sense. Yes?
So could we put f of x right there too?
Yes, I'm sorry. So this would be f of x. Would have been this. Yes.
Isn't it big F? or
It will be.
s?
But notice here I said f prime. One step at a time. Okay. We'll get there. I'll get to the point where I'm saying big ass f. Has anyone done 2a? Looking at that.
5x.
This one's kind of nice, right? Because this is exactly the opposite of something.
X of this.
Where did this come from?
Plus c.
Plus c. I love it. So real quick, what if I had f prime was 10 x to the 4th? What would f of x be?
5x to the 5th plus c.
Not quite.
2x.
2x to the 5th. Do you guys see that? Alright, I'm not going to write the general form yet. I will in a bit. Okay, don't say anything. Well, this shouldn't be that evil, right?
Negative cosine.
Yeah,
C.
this is where things gonna suck a little bit. This is where I can hear the gears when you gotta. So differentiation is going forward. If anybody's ever learned how to drive stick and you go to reverse, you sometimes you're like, oh shit. So I can hear that, so I can see smoke coming out. Sine and cosine suck because you've gotten so used to the derivative of sine is negative cosine. But now, when you're anti-differentiation,
It's backwards.
that flips, right? So what is the antiderivative of sine?
Negative cosine.
Negative cosine x?
Plus c.
Plus c. How do you check when you do antiderivative? How do you check your work?
Take the derivative.
Take the derivative. It's crazy. So the plus c always goes away. In case you forgot why we have to plus c, because if it was there, it would have gone away. So just cover my ass. How would I figure out what that was? I'd have to be given more information. If somebody told me, oh yeah, f of 0 was 7, then I could figure out what c was. Yeah? Okay. Oh yeah. Part D, did I give you anything anywhere that would have helped you figure out part D? Because that one, if I just asked you to do this one, without any prep, you could not do this yet. Well, maybe some of you guys could figure it out. This is more complicated. This is not just a straight up undoing a derivative unless you happened to have just done a derivative directly related to this. Did you do that? Did you just happen to do a derivative? Did you not? Is it on this very worksheet?
Number.
Yeah. The total.
Yeah.
So the answer can't be this, correct? Because if it's this, what ends up in front? 4. So what must, it's not this, it must be this with what in front?
4.
If it doesn't, if it has a 1 up front, I get a 4. I want a 12. So what must have been here? 3. What do I get if there's a 1? Don't I get 4?
Yeah.
What if there had been a 3 here? I would have ended up with times 1.
But don't you have to bring the?
I love you guys so much.
Don't
Okay.
you have to increase the?
You have to do any of that shit. No.
You don't have to increase the exponent
I need
by
this
1.
to be understood. If I gave you a problem like this, but I didn't have this anywhere on the same piece of paper, you currently could not do this. If you just happen to know, oh yeah, I took a derivative of something like that, so I know it's the answer must be what I started with. Then we just got kind of lucky. Real quick, if I would have put a 3 here, would this have been a 3 times 2?
Yes.
2x times 3 times 2 is?
Oh,
Because it would have been 3 times 4 at the end, correct?
yes.
So, yes, sir.
Could we not have boiled this out and then just antiderivatives?
Sure. We could have, but we don't need to. Because I gave you this on the same piece of paper. So what is it?
3
plus 3 squared to the third. Wouldn't it be c there?
To the what?
X squared plus 3 to the
No,
third.
because you didn't do anything.
No, it wouldn't be.
You didn't do anything with exponent.
Why you?
Oh, I see.
You bring the exponent
bring-
down
Oh,
anyway.
okay. This is my fault, guys. Is this why people are worried?
Yes.
This is a typo on my part.
To the 3. Oh, you did.
Yeah. I was looking at it the way I intended it, and then I'm like, oh, there's a 2 there. So that's my fault.
Wait.
So who said you should FOIL it out? Stuff? Okay.
Yeah, different answer.
So there should be a first power there. I'm sorry.
So I wasn't going.
Okay.
Can't believe Jeff made a mistake. How dare
Yeah, I
he
was
be
gonna
human
say,
for
I
a
was gonna
second?
say.
Prank.
So I wasn't going.
Little math prank.
That's my fault. I'm sorry.
Little
Yes.
math
Even
prank.
if you didn't have that one at the top, couldn't you still figure it out?
Yes, that's what I said. You
Okay.
could still figure it out. It's just easier when you have one that already
Okay.
done this like yeah.
I thought you were saying it was impossible.
No. I'm just saying where most of us are at the moment, it probably would have been really difficult until you get more practice. So this guy, okay. So let go of that. That's my fault. I'm sorry. Little typo. Jeff is
No, letter to editor.
question mark? Okay. This is secant squared. Where did it have to come from? I know part of my answer has to be what?
Tangent.
Tangent. I know part of my answer has to be tangent. I know the inside can't change through a derivative. It gets its own term separately, correct?
Mm-hmm.
But I know that this can't be the answer, not just because I didn't put a plus c, but why else can this not be the answer?
Because if you take the derivative, then the 3 would come out.
I would get a multiple of 3 out here, correct? If I take the derivative of this currently, there would be a 3 out front. There isn't a 3 out front. What must have been there that would kill that 3?
1/3.
1/3. I need you to notice something. I'm trying to force you to start looking at this in the right way. Do you see how I focused everything on the fact that it was a secant squared? So I know it had to come from tangent? Do you see how then I could just make the numbers work? Because of course I can. I could just figure out backwards what must there have been there, because there would be a 3 there, but there isn't. There must have been a 1/3 that killed it when the poor little dude came out. It's like, I'm free, and then he dies. Right? Very sad story, but you know, it happens. I don't know if you guys are with me on that. But. So of course when the inside gets more than just x, derivatives are worse, which means antiderivatives are even a little bit worse than that. Just because that's the way it is. It's just I'm doing something backwards. Are inverse trig functions worse than trig functions? If you don't think they are, you're an interesting person. I want to teach some more. Okay. All right. So, 4.9 is all about antiderivatives. Just got to give us a little preview where we're headed. So 4.9 is all about antiderivatives. You're going to see a lot of plus C. Let me do something like Sarah was reminding me about. I wanted this sheet to be something that was more like what we're used to. We're used to having f prime in our work, and then having f, it comes from f. Let me ask you this question. Couldn't every function you've ever seen, couldn't it be the derivative of some other function?
Yep.
Couldn't it be the antiderivative of some other function? Yes. So, let me give us a nice easy one to introduce this idea. What if I had, you can do it, Jeff. This here. Do you notice how it doesn't have a prime on it, correct?
Mm-hmm.
But who cares? It could still be the derivative of some other function. So what we do in this case, I can't just take the prime away because there's no freaking prime to take away like we just were. So what we do in this case, you probably overheard me say this a second ago, we call the antiderivative capital F, which I affectionately call big ass F, right? So if there was a prime here, we would just write F, that would be the original function. If this is not prime, when we take an antiderivative, we just make it capital F. So this is a function, and this is a function. So what would this be?
X to the fourth.
Good?
X to the fourth, less natural log x, plus c,
Natural log of what now?
Absolute value F.
or absolute value x.
Okay, good. I want to get you guys really used to that because it's going to save your ass in the future. You're going to have some shit where you got to plug negatives in, and if you get the absolute value, you're going to think it's not good, but it should be good. Yes?
So you said that if it was a derivative function, we don't need to put the big F to go back.
Yeah, just like we did on the handout. So watch this. Watch this. If I start with f and I take a derivative, that's f prime. Yes. Sorry, you can't watch it unless I show you. If I take another derivative, it's f double prime. Correct.
Yeah.
Another derivative is what?
F triple.
Holy shit! What's another derivative?
F.
F
Fourth.
4 in parentheses. Yes. And then I can keep going forever. If I go backwards, then it's big ass F. Above that, it would be bigger ass. No, we just don't do that.
It would
Sure,
be-
we don't. We just give up after that.
Yeah.
We just do one level of that kind of shit. It'd be big ass F unprime or something. It's the uncola. I don't know what it would be. But I like to think it would be
Just
bigger
start
ass
going-
F.
Just start.
But
Just start going backwards from the alphabet.
we only use big ass F very limited. For just a little bit, and then we just sort of talk about the integral, and we introduce other notation. I just said a word I shouldn't have said, but integrals, yeah. So we use other notation to identify antiderivatives. That's in our future. Right now, we just do one step back for big ass F. We don't have another step to go back. We could, yes.
So are we gonna be? Do we have to know how to go from like second prime to the original?
Yeah, sure. Okay, watch this. If f triple prime of x was what, Jeff? I don't know. Secant x tangent x. What was f double prime of x?
Secant x
Yes?
plus c.
Yes. There you go. So if I go one step back in the levels of derivatives, that is antiderivative. It works. So from f prime to f is the same as from f to big ass F is the same as from f triple prime to f double prime. You guys with me? Because that's just one uncovering of differentiation, one undifferentiation level. You with me? They all are the same freaking thing. Any function you've ever seen in your entire life could have been f seventh derivative of x, of some function. You don't know. You don't know. Yes?
Just out of pure curiosity, could you go back one more step?
That gets nifty. The antiderivative of this is nothing that is very obvious. Does anyone know the antiderivative of the secant of x? It would be the thing whose derivative is secant.
It would be secant x.
Square root of tangent.
It is really trippy. So one way you could do it's I never want you to take this wrong, but you would never guess it. Okay, it's nothing obvious, right? It is nothing obvious. No. How do you check it if you have a guess?
You take the
Derivative of what you think the answer is. So if you want to, go for it. Well, obviously talk about it eventually, but right now we're just introducing the idea. We're not going to do shit like that yet. There is a way to do this. It's in our future. We're not there. Alright. It's like if on the first day of differentiation I said, let's do the derivative of the inverse tangent natural log of that. No, we just weren't ready. Okay, you're not ready. You can't handle it. Okay, so what we're about to get into is interesting because it kind of makes sense. At the end of chapter 4, before we get into the full-blown second part of calculus, we have this little section that's just like, okay, you know derivatives. You only know them if you know them backwards and forwards. Right? That's basically what 4.9 is. Oh, you think you know them? Do you know them backwards? Okay, then you know them. What's really weird is, and I really want this to make sense, we're about to take a very hard turn. 5.1 is going to suddenly seem like it's completely its own thing. I just want to let you guys know. And then, I desperately want you to understand, we're going to do several sections of this weirdness. And then we're going to go, oh yeah, remember that shit in 4.9? We're going to tie that into what we're doing to give us a shortcut. Okay. What we're about to get into is kind of the equivalent of the limit definition of derivative, which I'm certain makes you all very excited. It just involves summation symbols and such. Finding areas, which sounds good. Areas of rectangles, guys. How do you guys feel about areas of rectangles? You know, like, generally okay, unless you're asking me, and then... So let me ask you this. Oh, shoot, I didn't bring it. That's too bad. If I wanted to estimate, so let's say I have this parabola here, right? And I want to estimate its area. Could you estimate the area inside this parabola, between the x-axis and the parabola itself? Could you estimate it? You could do it, right? Isn't it 1 square unit, 2 square units? And then you have to kind of like estimate for these, right? This is not quite a full square. Do you guys see what I'm saying? Do you see, couldn't you do it? What we're going to get into is, I want to know the exact area under that. And I want us to be able to calculate that by hand. And it's not going to involve estimating squares and going and saying thank to God. But I like this idea for the first level of what we're doing. So let me ask you this. Has anybody ever, like, let's say I ask you, how many of these fit into this shape? Couldn't you just cut out a piece of this and just start laying it on here? So if this was like 1 square centimeter, and I want to know what's the area of the shape, couldn't you just take this couldn't you just cut a bunch of those out and just put them in? Does that make sense? Would it be exactly right? Would it be a really good approximation? Yes. Because you might overlap a bit. You might have a little bit of your square going outside of the thing sometimes. Sometimes it'll go in. Overall, it's going to sort of average out. You guys kind of see what I'm saying? So what we're about to do is we're going to answer the question, if I have this function, and I want to know the area between the x-axis and the function, couldn't I break this up into rectangles And you see how the rectangles are not gonna be perfect? Couldn't I find the area of each rectangle and add those up? And wouldn't that be a decent approximation? For what the area, I want the actual area under this weird shape. And it's not a circle, so I can't use pi r squared or shit like that. I don't have a formula for it, a freaking parabola area. I just don't. Do you agree with me? From the way I've drawn this, would my answer of the areas of the rectangle be bigger or smaller than the answer that the area of the parabola?
Bigger.
A little bigger, because most of my rectangles are like is outside of it, right? They're kind of going over. So there could be an overestimate or an underestimate. Yes? I just want this idea to make complete sense. So is it hard to calculate the area of a rectangle? Especially because I made them. I would know how wide they were, correct? And then I can figure out, what am I gonna determine how tall it is? And I want you to notice, I didn't do this on purpose. This is kind of so not on purpose, it kind of sucks. But do you see how this guy's height seems to be its midpoint? And where that is on the parabola? But you see how this guy's height seems to be this side of it? So I really want this to make sense. I want to put rectangles, but I want them to be based on the function itself. So the height of the rectangle is going to be based on the function, and I want to do it in a much more formalized way than I just did that horrible shit. Maybe I want every rectangle's height to be determined by the left side of it. So for example, if I'm going to stick with this shape. So the left side of it here would be flat, yes? The left side of it here is 0, is that cool? And then if I start the next rectangle, it would go up to there, is that all right? Do you guys kind of see what I'm saying? The left side of it determines how tall it is. Does that make sense what I'm saying? The left side of it determines how tall it is. The left side of it determines how tall it is. The left side. So what am I going to do on the other side? I'm going to start to overshoot it, yes?
Yeah.
So overall, maybe this averages out pretty well because this little bit of overshootage fills in the undershootage just to make up a little bit. It's probably going to be an underestimate because I'm missing a huge chunk of it. But you guys start to see the idea. I want to formalize this because considering, do you guys think that would be a decent estimate? Yeah. How many rectangles do I have? 10? Okay. So if my parabola went from 2 to, you could do it, Jeff. I don't know, Jeff. 2 to 32. Can anyone tell me how wide each rectangle should be? 3. Does that make sense? I have 10 rectangles, and I want them to go how far? 30. So I would make each one of them have a width of 3. Does that make sense? So I'm determining the physical characteristics of your rectangle according to the function I'm trying to approximate, which only makes sense. How would I make my approximation better? Make the rectangles smaller, because then what do they do then? They fit in better. I'm kicking up my resolution. How do I make the answer perfect?
Infinitely smaller.
How many rectangles should I use to make it perfect?
Infinite.
Infinite number of rectangles. Are you with me? Do you guys want to draw an infinite number of rectangles?
No.
That
You
makes
could
it-
never reach.
The whole cell. Yeah.
Exactly. So what idea do you think we're going to incorporate? I like it. So just when you thought they were gone, we bring them back.
Mm-hmm.
Okay. So there's going to be a limiting process that will get us the area under a function. So has anybody ever taken statistics before? Anybody?
But I have to.
And even if you haven't taken statistics, does this shape look familiar?
Mm-hmm.
You've seen it on my shirt. I think I've worn it. I can't remember if I've worn it here, but it's the bell curve. It's all called a normal distribution.
Top of the bell.
So basically, the area in this determines the probability that, for example, if these are heights. Somebody's between 69 inches and 74 inches. If I get the area, it tells me with a percentage of people that would be between those heights. And then I can figure out how tall I want to make the door so that only a certain percentage hit their head on the way else. Right? You guys, I'm not gonna suddenly teach you probability, don't worry. Is that a shape that you have a geometrical formula for its area? Do you have the area formula for a crayon that's been out in the sun? No, one side of it, if you do, write it on the board. One side of the damn thing is curved, are you kidding me? Is that a parabola? No, it's a ghost. Are you kidding me? What is that? That's called a Gaussian curve. Whatever, Gauss, you did too much shit. You should have left something for other people. I don't have a freaking formula for that. So, calculus, the second half of calculus, is undoing differentiation, which makes sense, because we always have to figure out the opposite operation. But it ties that to calculating the area under a curve, between the x-axis and the curve. Are you with me? That is so stupid important. In fact, if you go any further in STEM or math or any STEM, you're gonna start to go, how did I do shit before I knew calculus? And if I haven't said this to you yet, calculus is where math starts. This is where math starts. If you go any further, you're like, oh, that's when I finally started doing math, was calculus. And I don't say that to belittle pre-calculus, because pre-calculus is hard. But this is what everything is based on. This is what some of the shit you guys have used is based on. You can finally prove it once you get to calculus. So, okay, I'll stop. I just want you to understand what we're about to get into is remarkably useful. At the beginning, it's going to be a little funny because we're going to literally be doing problems where I'm going to have you drawing these in, not an infinite number, maybe 6, okay? And you're going to be calculating the areas of each one. There's going to be your approximation, blah, blah, blah. Okay, so that's going to be our life for a little bit. And then we're going to connect this with antiderivatives so then we can make a shortcut. I don't want to do this shit for every function. I want a shortcut, please, dear God. So we'll get there. Okay, that's enough. I'm sorry, go ahead, Louis.
The function went down and then it went back.
Yeah, the neat thing is, area can be negative.
Makes a reference point at the bottom.
This just means I'm losing. So if this is my profit function, my rate of change of profit function, that would mean if it goes negative, that means I'm losing.
You subtract that from the
So I would subtract it from the total. So negative area. You'll talk to some of my colleagues and they'll disagree with me, but I'm completely cool with negative area. Because it just means I'm losing whatever that's measured.
So wouldn't the area of sun just be
Well, if you go from like 0 to 2 pi,
yeah.
if you go from like pi over 4 to pi over 3, no. You see what I mean? So it totally depends on where you're going from to. Because I could have done this from 2 to here.
Yeah.
And not considered this.
Right?
Yeah.